All right, in lesson 4, we're going to switch gears a little bit. And now that we know how to do the basic math of current electricity, we're going to talk about the form that current electricity normally takes, and that's called a circuit. I'm sure you've heard of a circuit before, and while circuitry itself could be an entire major in college, we're going to spend just a little bit of time to talk about the basic parts of circuits. So first of all, a circuit is defined as a continuous path on which electricity flows. You can kind of think of it as a racetrack, right? Electricity just keeps going around and around and around with no gaps, nothing else interfering with it, just around and around and around. All circuits require 3 things. This is a big one, so stars highlight something around this. This is an important concept. All circuits require a conductor, right? Usually that conductor is a wire. However, with nanobots coming out and new circuits, we're using liquid metals, we're using writable pens, anything that can conduct electricity. I believe in 7th grade you even did it where you put the 2 paper clips in salt water. That was a conductor, so you need at least one conductor for a circuit to continue. What you hope is that the conductor isn't you, because that'd be bad. You need some kind of an EMF or voltage source. From here on out, I'm going to use the word voltage. So you need a voltage source. So usually that's a battery, an electrical outlet, high voltage wire, static electricity generator. Usually not, because very rarely do you use a static electricity generator to complete a circuit, because that's a continuous flow, but it could be a voltage source. And you have to have a resistor. Now this doesn't quite make sense if you think about it, in just terms of basic parts. This is a little counterintuitive. You've got to have something to slow down those electrons. Must be there. The resistor, the thing that creates resistance, is the whole point of having a circuit in the first place. All right, so what does that mean? We said that all current electricity is man-made, meaning that man put together this circuit for a purpose. And the purpose, guys, is to do work, is to complete some task that man itself either cannot do on their own or could only do on their own with great difficulty. So the resistor is the thing that we want it to work. Okay, perfect example of a resistor is a toaster. Okay, let's use a toaster. Let's pick on the toaster. All right, so a toaster heats bread, right? That's its job. It makes toast. Now, it does that by slowing down the electrons so much that they give off their energy as heat inside the toaster, and that heat heats the bread. So, could we toast toast without electricity? Well, yeah. We could take a stick and we could put a piece of bread on the stick, and we could go over an open flame, and we could lightly swipe the bread back and forth until it's acquired a light golden brown toast. But that's annoying. And that takes a lot of time, and who has time to build a fire in their backyard for a piece of toast in the morning? I don't have that kind of time. You don't have that kind of time. So the toaster was invented to do work for man that we could not do otherwise. Now I realize that the toaster is not man's greatest invention, and I don't mean to sound like that, but it's a perfect example of why a circuit needs a resistor, because a resistor does work. All right. So the point of the resistor is to slow down the electrons. When the electrons slow down, in other words, when they're given resistance, they often lose that energy to the resistor, and then the resistor uses it to do work. So that's what that next bullet means. Energy from electrons is transferred to the resistor to do work. If you do not have any resistance in your circuit, you have what is called a short circuit, and we will talk about that a little bit later, but that's bad. All right, so when we're drawing circuits, we use what is called a schematic diagram. That shows the flow of energy. It can also show the flow of electrons. We're not going to get into the distinction in this class. You will next time you see physics. Circuits are always drawn with right angles. Now, that's a little antiquated. It's kind of a traditional thing now. We generally draw circuits at right angles because when circuits were first being drawn on the earliest computers, there was no way to draw a curve on a simple dot matrix monitor. So we still draw them with the right angles. But you got to understand that a right angle in a circuit doesn't necessarily mean 2 wires. It just means that's how we've always drawn them. And we don't use English words or numbers. We use symbols, universal symbols. This is because circuits are often interchanged between countries. Think about that. Think about a car. You've got a German engineer, right, who's building a circuit for a computer that goes in the dashboard of a BMW. That computer circuit has to connect to a mainframe that's being built in the United States with electrical parts that were manufactured in China or Japan. So everybody has to be able to read that drawing, and the people in Japan don't speak German, the people in Germany don't speak English, the people in America don't speak Japanese or German. So we have to use them. If you've ever been to an international airport, you know exactly what I'm talking about, right? Like this one. What's that one? That's baggage claim, right? You got to know where your bags are regardless of where your plane lands. This one, first aid, medical attention, I know where to go. And this one, obviously, maybe some of you don't know what this one means. It's been so long since you could do this anywhere. No smoking. Right? So you see these signs, and no matter what language you speak, you know what they mean. All right? So circuits have the same kind of universal symbols. You will need to know these and how to draw them. So let's take a minute. If I can find my, pen. All right. So the universal symbol for a wire is a line. And the line can be drawn this way too, but that's the universal symbol for wire, line. An EMF source is drawn with a long line and a short line. Right? It doesn't matter for our purposes which one is which or which way they go. Depending on how you're drawing your circuit, you can also draw them like that. A long line and short line. Be careful here. You do not want to draw your lines the same length. That means something else in a circuit. A switch, something to turn a circuit on and off, you draw like that, like a little drawbridge open. No matter how the switch is positioned in our circuit, we always draw it in the up position so we don't confuse it with a wire. A standard generic resistor is drawn like this, almost like speed bumps because they are slowing down the electrons. Light bulb, now a light bulb is a type of resistor, but it has its own special symbol. It's that. I've even seen it drawn that way, but like a little circle around it. Either one is fine. An ammeter, we're going to talk about what an ammeter means a little bit later. Ammeter is something that measures current. It's an A with a line across it, and these lines are wires connecting to the ammeter. A voltmeter is basically the same thing with a V. A motor, you guessed it, M. A fuse. Okay, now a fuse is something that will break a circuit. And we're going to talk about what those mean in a second too. It's a squiggly line, kind of like a Pepsi, with a circle around it, like that. And then a circuit breaker. Now there are some other variations of these. Not everybody uses the exact same drawings, but these are pretty universally held, and these are the ones that we're going to use. So you need to learn these circuit symbols. Incidentally, if you haven't noticed yet, these symbols are also written out in one of the back flaps of your lab notebook. Okay, now a simple circuit is just one voltage source, one resistor, and some wires that connect the two. Easy peasies. We're not even going to spend time on that. Let's talk about what a series circuit is, because this is one other type of circuit you're going to see. A series circuit is a circuit with two or more resistors in the same path of electrons. So check out what I have here. All right, so here's my EMF source, right, my battery. Like you can see, here's what it would look like in real life, and here's how I would draw it. So here's my battery, right there, okay? Then I draw, again, this is one wire coming all the way around. It's just bent because we normally draw these at right angles. So bend. All right, here's my first light bulb. That's a resistor. So resistor. Then I have a wire connecting the two to the next resistor. Wire, resistor. Then I have another wire connecting the next resistor. So wire, resistor, and then back to the battery. All right? You can kind of think of a series circuit as everybody leaving convo, and that's what this picture is supposed to be, like everybody leaving all school convo out of like the same door. You've got lots and lots and lots of people, just like you have lots and lots and lots of electrons, all trying to cram into one tiny little door. All right, so obviously their flow or their speed is going to get slowed down as they get through those doors. All right, so current or the speed of the electrons is going to decrease, and that is because resistance increased. Right? They were all mulling around, but then they wanted them to squeeze through this tiny door, so your resistance to them getting out of the convo just suddenly increased. So with a series circuit, resistance is high and current is low. Now, how do we figure out the total resistance in a series circuit? Well, this one's as easy as it gets. For total resistance in a series circuit, all the resistors are going to add up. Okay? So if my first resistor, so if I had something like this. Sorry, it's hard to draw on this thing. Alright, and I had a 5 ohm resistor here, and a 3 ohm resistor here, and a 2 ohm resistor here. And I wanted to find my total resistance. It would be RT equals 5 plus 3 plus 2. So my total resistance would be 10 ohms. This is the number that I would use to represent R in Ohm's law. So if this was a 5-volt battery, V equals IR. So 5 equals I times 10. So divide both sides by 10. And I is going to equal 0.5 amps. Alright, so how about you try one? Stop this recording for just a moment and give this a try. And then I will be back to work it out with you. Remember, 5-point problem setup every single time. Okay, how did you do? Let's see. Alright. Now this one has a little bit of a, this actually has 2 tricks. Let's take a look. Alright, first I'm going to find my numbers. 1, 2, 3, all resistors, and they're all connected in series. So first off, I know my total resistance is resistor 1 plus resistor 2 plus resistor 3. So my total resistance is going to be 15 plus 5 plus 12. Right, so that means that total resistance is going to be 32 ohms. Okay? So now I'm looking for the current. So now I have an R of 32. That's what goes into my formula. I have an I don't know. Okay, now wait a minute. I need a voltage. I don't have a voltage. This is the first time of many where you're going to see that some numbers are hidden by words. All American outlets have a voltage of 120 volts. We'll learn more about that in the next lesson. So these words actually mean 120 volts. So now it's V equals IR, 120 equals I times 32. I'm going to divide both sides by 32. And that means when we round to the 10th, I equals 3.8 amps. All right, the other type of circuit we're going to talk about are parallel circuits. Parallel circuits are a circuit with 2 or more resistors on 2 or more paths of electrons. All right, now this is different. When we were talking about series circuits, all of the resistors were on the same path. These guys are not. Let me show you what I mean by that. All electrons want to complete a path back to the battery because the battery is where the plus charge is that they desperately want to get to. Actually, let me use a highlighter. All right, so starting at my battery, I go up and around and down and back and there. That is one complete path from the battery back to the battery through this resistor. Now electrons cannot go backwards. It's always a one-way street. So now notice that I could get back to the battery without going through this resistor or this resistor. That is different than in series circuits where I cannot get back to the battery without going through every single circuit, every single resistor rather. So let's take another look. Let's look at a different highlighter. Let's go to green. Okay, here we go. Here's another path back to the battery. This time, I didn't go through this resistor. So that means that the resistor here and the resistor here are on two separate pathways back to the battery. And just to kind of round it out, this is a third pathway to the battery. So this resistor, and this resistor are all on separate paths. So if you can draw a pathway back to the battery without going through all of the resistors, then you have a parallel circuit. All right, just kind of to ram that point home, this is my series circuit, and I can't see that color, so I'm going to get another one. I can't really see that one either, but the only way to go back to the battery without overlapping or going over the same place twice is to go through every single resistor. That is a series circuit. Going through different paths is a parallel circuit. Right? Kind of like if you have a home here where you can actually take two different paths to get home. Like from here to here I can take this street or I can take that street. Now, just like in a series circuit where all the electrons are being forced on the same path, that means that that's going to increase resistance and slow everybody down and decrease current. If I have multiple options to travel on, then my resistance is going to decrease and my current is going to increase. Imagine again, if we're at Convo and everybody says, okay, you're dismissed, but instead of one door, there are multiple doors. That means people are going to scatter to the closest available door and the gym will clear out quicker. So that means speed will increase because resistance has decreased. If this does not make sense, that is okay. We're going to do a lot with this in class. So make a little note on the side here. I'm still not quite sure about resistance and current and parallel and series circuits, and that is okay. We're going to do a lot of this review in class, but make a note so you remember to ask me about it. Okay, this is the hardest math we're going to do all year. All right, so everybody's listening, everybody's watching. Last thing we're going to talk about is how do we figure out total resistance in a parallel circuit. Instead of just adding up all the resistors, we need to turn them all into fractions and then add the fractions. And remember, when you add fractions, denominators must be equal. Denominators must be equal. And then look at this. My answer is actually a fraction too. So if I want total resistance at the end, I have to flip my 1 over RT. All right, let's take a look at what that looks like. So 3, there's a number hidden by a word. 5 ohm light bulbs are connected in parallel to a 7-volt battery. What is the total resistance and current of the system? So let's do total resistance first. Let's draw this circuit so we can see what it is we're talking about. Battery, 3 light bulbs. Light bulb number 1, light bulb number 2, light bulb number 3. That is a parallel circuit. Sorry, all those should connect. All right, this one's 5 ohms, this one's 5 ohms, and this one's 5 ohms. And this one is 7 volts. Okay, so first thing I've got to do is find my total resistance, my RT, because I can't do V equals IR unless I only have one R. So 1 over RT equals 1 over the first resistor plus 1 over the second resistor plus 1 over the third resistor. So now we're going to add these fractions. So remember, when we add fractions, our denominators must be equal to start. And in this case, our denominators are equal. So 1 over RT. Now, that means that in our answer, the denominator stays the same. Remember, we don't add the denominators. It stays the same. We add the numerators. So 1/5 plus 1/5 plus 1/5 equals 3/5. And the last thing we have to do is flip. So RT equals 5 over 3 ohms. So now we can do our problem. Here's my voltage. My total resistance is 5/3, and I'm looking for a current. So here we go. V equals IR. 7 equals I times 5/3. So we're going to divide by 5/3. And 5/3 is the same as, if we were to put that into decimal form, that's the same as 1.7 ohms. So 7 divided by 1.7 equals I equals 4.1 amps. Okay, that's a lot of math. Take it slow, go through the process, and see if you can't get to the same place I'm at. All right, last thing we're going to talk about in Unit 1-4 is how we break a circuit. We've been talking about how circuits are a continuous path of electrons. To break a circuit, you need to open it. It's like a drawbridge. Like a road doesn't work at a road if a drawbridge is open. So, opening a circuit breaks the path. The electrons cannot flow because you've introduced air. And as I've said a million times, air is a great insulator. So the path flows, so the path becomes off. So now your circuit is off. That's when the light goes out. You've introduced air. A closed circuit is when the drawbridge is down, so the continuous path of electrons is on. So here, if you bring the switch up like that, there's air here. This is now open and off. But a closed path is straight across. That's going to be closed and on. A switch is what can actually do this. It is a reusable break in a circuit. Remember, we draw it like that, always in the open position. A circuit breaker is a reusable break, but that's triggered by a current overload. So it has a little ammeter inside. So if this little box here reads that the current is too strong, it'll automatically flip a switch. Here, just a regular old switch, you can flip whenever you want. And a fuse also works by an overload of current, but it's not a switch. It's actually a little piece of metal that snaps, and it is non-reusable. Once it trips, you have to get a new fuse. Again, it is okay if this is not 100% clear, because we will be going over this in class with lots of examples. I even have some example circuits and fuses for you to play with and see. How does a circuit know to shut off? Well, it shuts off by an ammeter. An ammeter will measure the current or speed of electrons. This is what your ammeter looks like. It measures in milliamps, and there's really no resistance in an ammeter, so it always has to be connected in a series. So like this. If we were to measure voltage, we would measure it with a voltmeter. Now, a voltmeter also measures in millivolts, but it could also measure in volts. It carries with it lots of resistance, so it has to be connected in parallel, like this. So it has its own pathway back to the battery. All right, so those last two, the ammeter and the voltmeter, again, this is just a broad definition. So these last three slides, it is okay if we don't 100% understand what is going on here. This was just an introduction so that when I show you in class, you'll at least know a little bit of what I'm talking about. But our 1-4 activity in class is to pull all of this stuff out and give it a shot. So again, do not worry if how to use an ammeter or voltmeter is not 100% clear. That is where we're going to pick up in class. All right, so now you have everything you need to finish 1-3 and 1-4. Go ahead and do the questions for 1-4, but do not worry about the next page in your booklet yet that says circuitry problems. Wait on those. I just stapled them so that you wouldn't lose them, but that is the next homework assignment. only worry about the one page that says 1-4. And that was it. Thank you for watching, and I will see you next time.